All right, so let's get started. Today, the thought is to finish off the physical layer and then start to talk, walking up the stack a little bit. So today we will talk a little bit about symbol error probability and bit error probabilities for PAM and QAM. Quite quickly, I would say, to go over to the bulk of the material, which is about error detection. And error detection is a crucial part in the data link layer, as we will see later on, for retransmission protocols that we will start to talk about next week. And for project part 1, it's pulse amplitude modulation, so you should be able to do that right now. Part 2 is about the retransmission protocol, and we will talk about that the coming week. Okay, so short review on what we have done. We talked about pulse amplitude modulation. We talked on how to classify noise as being a random process. We also talked about the data is random from at least from the perspective of the receiver. The transmitted data is random. We arrived at the error probability for pulse amplitude modulation, MRI, PAM, where we have some noise with the Gaussian noise with the power spectral density n0/2, and then we have this expression. We will interpret this in graphical form a little bit later today. And then, if you remember, pulse amplitude modulation is when we put the signal points along one line. So we have signal points along a line like this. QAM is basically when we have two parallel PAM systems, one in one direction and one in the orthogonal direction like this. And the actual signal points that we transmit is a combination of these two. So actually there's the green points that we are transmitting in this case, which is composed of the red and blue points like this. So in this case it happens to be 16 QAM, 16 green X's. There are 4 PAM along this direction and 4 PAM along this direction. 4 times 4 is 16. Okay, so for a system, this the green one here is a QAM system, and the blue and the red ones here are 2 PAM systems. So with a little bit of, we will actually see this a little bit later. With a little bit of manipulation, one can calculate the error probability for QAM, and it looks like this. It looks a little bit more complicated than it actually is, right? So we will dissect that a little bit later. Okay, and then we will talk about bit error probability in gray coding and so forth. So symbol error probability for PAM. Typically, physical layer performance has to do with symbol error probability or bit error probability or some error metric as a function of the signal to noise ratio. So for higher signal to noise ratios, we expect better performance and vice versa. This is a very typical plot where we have, in this case, error probability like this, and it's plotted in symbol error probability, and it's plotted in logarithmic scale, as you see here. So this is 1%, this is 10%, and this is 1 per mil here. Right? So it's a logarithmic scale here. And on this axis, there is some type of signal to noise ratio. It could also be transmit power, because these are proportional to each other, or some other metric that shows the link quality. The higher the signal to noise ratio is, the better the medium is. And typically these are plotted also in logarithmic scale. So ES over N0 is known as the SNR per symbol. ES because it's energy per symbol, right? If it's EB over N0, it's the SNR per bit. So this is the SNR per symbol, the EB, ES over N0. So ES over N0, SNR per symbol. And if we take the 10 log 10 of that, we get this in decibel scale. So this is in dB. So, I mean, it's a dimensionless unit here. So it doesn't have a unit, but when typically we plot this in logarithmic scale, the 10 log of the SNR times 10, then we get it in dB. Okay, so then we can start to plot things, and if we start to plot performance when m is equal to 2, that is, we transmit 1 bit per symbol, then the symbol error probability decreases as we expect it to do, as the signal to noise ratio increases. Okay, so we get a certain spectral efficiency, and the spectral efficiency, we computed that earlier to be the 2 times the log 2 of m. Log 2 of m is the number of bits we transmit per symbol, and then divided by 1 plus alpha. And alpha is the factor that determines the excess bandwidth, the extra bandwidth we need in order to support ISI-free transmission over the medium. Okay, so we assume that all of these schemes use maybe a root raised cosine Nyquist pulse or something like that, or some other Nyquist pulse. Okay, so the spectral efficiency only is determined then by log 2 of m. So when we increase m, we increase the spectral efficiency. So ideally, if we go from m equals 2 to m equals 4, we transmit 1 more bit per symbol, right? And if we go from 4 to 8, we transmit 1 more bit per symbol. So here's 1 bit per symbol, 2 bits per symbols, 3 bits per symbols, and so forth. And you see, of course, that the number of signal alternatives is 2 to the power of number of bits we transmit per symbol. So they increases rapidly with the number of bits per symbol. And we also see that if we want to reach a certain error probability, say 1%, how much SNR do we need in order to do this? Well, we just draw a straight line like this, more or less, and then read off the corresponding SNR we need for m equals 2, m equals 4, and so forth. And we see here that for as m increases here, the signal to noise ratio requirement to get a certain error probability increases rapidly. Right. As a matter of fact, okay, and of course we would like this to be as far to the left as possible, because that means we can have a smaller transmit power, which means that we save battery at the transmitter if that is important, or otherwise we use less, transmit less energy, which is always used. Good, less heat in the transmitters and so forth. Right? So we want to be to the left, but we also want to have m equals high. Right? So there is a compromise between these two things. So the power efficiency decreases when we increases the spectral efficiency. So to reach the same error probability costs approximately 6 decibels per extra bit. Okay, so what is meant by that? Well, if we take a relatively low error probability and we see the difference between m equals 4 and m equals 8, that is 6. Okay, and the unit is decibels. So there's 6 decibels difference between these two things, these two curves. And there is another 6 dBs difference to go to m equals 16. So 2 bits, 3 bits, 4 bits. Okay, so it costs you 6 dB for each extra bit per symbol that we want to transmit. Okay, so is this significant or not? Well, yeah, I would say so, because 6 dB, that means that is 3 plus 3. 6 is 3 plus 3 dB, right? And 3 dB is a factor of 2 times a factor of 2. So this is a factor of 4. So we need to quadruple the power by going from here to here. Okay, another factor 4 going here. So from here to here is 16 times more power, right? So it scales very badly, I would say. Okay, and this is, one can see this easily from the formula if one likes. We just look at the argument for the Q function, which is the important thing, and see how that scales. So any questions before we continue? Okay, so take-home message is like this, that if we want extra spectral efficiency, we have to pay with power. If we want to reduce power, we need to accept a lower spectral efficiency. Okay? Which one of these blue curves we choose depends on how important these two things are in relationship to each other. So there is not one solution, right? What is most important? Spectral efficiency or power efficiency? Well, that depends, right? Okay. So you select the modulation format according to this trade-off. Questions? No? Okay. So let's continue then. QAM, I already alluded to that QAM, we can see that that's two PAM signals, one in the one along one axis and one along the other axis. I will go through this quickly now because I want to get into the bulk of the important parts of this lecture. So I apologize to go a little fast here, but you could just read up on these slides afterwards. It's not rocket science, right? It's just a little bit of algebra. But the important thing here is that if we want to be, if we look at the decision boundaries here, we have decision boundaries that goes along that's parallel with the vertical axis. And then we have decision regions that goes along the horizontal axis, like this. Well, maybe I should draw this as green here also. So these are the decision regions. So if this signal is transmitted, we make a correct decision if we end up in this region, right? And to end up in this region means that we are to the right of this boundary and to the left of this boundary, which is then determined by the PAM along this axis. So if we look at this as a PAM, if we take the received point, say, and we then project it down to the horizontal axis here, we will make a correct decision in this along this axis if it ends up in the correct PAM decision region. Okay. And likewise, if we project it onto the vertical axis here, we will make a correct decision if we are on the right decision boundary for the vertical system here. Okay. So what I'm trying to say now is that we make a correct decision for QAM if we make a correct decision for the individual PAM systems, the one along this axis and the one along this axis. And if we do that, we can simply reuse our formulas for the PAM system and just insert that into these equations. Okay. So this is done here, and then one calculates and then one gets this result. And if we continue, we calculate the energy, relate that to the distance between two adjacent signal points, and blah, blah, blah. And then we end up at this final result here. Okay, so I skipped a lot of the algebraic steps here. Now, this expression looks more complicated than the PAM one, but we can make a few simplifications. And that is, as the signal to noise ratio, ES over N naught, as this becomes large, what happens with the Q function then? Does it become smaller or higher? Smaller, exactly. It's the tail of the Q function, right? So the larger the argument of it, the smaller the tail will be. So this is decreasing in ES over N naught. So if the Q function here is small, what can we say about the Q function squared then? It's the same argument as you see. So if this one is small, what is Q squared then?
Very small.
Exactly. So for high signal to noise ratio, we can forget about that term and then just look at this term, which is much simpler, and then directly compare that with the PAM system, if you like. Okay. And if we do, we get curves that looks like this. Again, we have the error probability in logarithmic scale here, and then SNR in dB scale along this axis. And then we have the PAM system in blue and the QAM system in red for different M's. So which one is the best here? QAM or PAM? QAM. And why is that? Exactly. So for the same M, we need less power for the red system compared to the blue system. So that's good. And they have the same spectral efficiency. Okay? So again, when one compares different modulation formats, one has to deal with both spectral efficiency and power efficiency at the same time. So I can get any spectral efficiency I like, but I will have to pay with power, and vice versa. Okay. So here, QAM is much better, and that's why it's used, right? So, I mean, this constellation here is just from the Wi-Fi standard, so it's a Wi-Fi constellation. So this is clearly used in practice. While you would never see a pulse amplitude modulated passband system, okay? For baseband systems, you would use PAM, okay? But for radio, you would not use that. Typically. Not if you care about power efficiency and spectral efficiency. If you care about other things, maybe you would see them. Okay. So that about symbol error probability. We also sometimes are interested in the bit error probability. So what is the relationship between bit error probability and symbol error probability? So remember that the symbol error probability is the probability that our estimated symbol, k is a time index here, is not equal to the transmitted symbol. Right? The bit error probability is the probability that the ith bit, the decision on that, is not equal to the ith bit that we actually transmitted. Okay. Now, if the symbol error probability is 0, then the bit error probability is also 0. Okay? Because the symbols carry bits. If the bit error probability is 0, then the symbol error probability is also 0. So they're connected somehow, but how are they connected? Let's figure that one out. Okay, so first of all, let's do an M-ary system where we have M symbol alternatives and we have k bits per symbol. Then, if we make a symbol error, okay, so this event has happened. AK hat is not equal to AK. Then, what can we say about the corresponding bits which were carried by the symbols? Well, we can say at least one of the bits is in error, right? Because not all bits can be correct, because then the symbol would also be correct. Okay. So a symbol error leads to at least one bit error, and at the most k bit errors. Okay. So if we have transmit 4 bits, and I know that the symbol is wrong, then I know the pattern is wrong. But the pattern is wrong if 1 bit is in error, or 2 bits are in error, or 3 bits in error, or 4 bits are in error. All of these constitutes a symbol error, right? So actually, it's a little bit hard to have a direct translation between symbol error and bit error probability for this case, because if we make a symbol error, some of the bits are correct. Okay. So now we can look at the extreme cases. Okay, when all bits are wrong for all types of symbol errors, then the bit error probability is equal to the symbol error probability, right? Symbol error induces all that all bits are in error, and then the probability for bit error and symbol error is the same. In the other extreme case, when only 1 bit error occurs, then we transmit. So I transmit 4 bits. This one is in error, so therefore there is a symbol error, but these 3 bits are okay. So then the bit error probability is only 1/4 of this symbol error probability, right? If no symbol errors, all bits survive. If there is a symbol error, 3 out of 4 survives. Okay, so then the bit error probability is actually only 1 over the number of bits per symbol multiplied with multiplied with the symbol error probability, like this. Okay, so in general, we have something which is in between these two extreme cases. So the bit error probability is always less or equal to the symbol error probability. It cannot be higher, but it can certainly be lower. And it's bounded from below by 1 over k times the symbol error probability. So it cannot be arbitrarily low, the bit error probability, because it's bounded from below here also. Okay, questions on this? In this course, bit error probability is not super important, but in other courses they may be, right? But we'll continue. So if you're interested in formal proof of what I hand-waved myself through, this is it. We'll skip that. How do we minimize bit error probability for a given symbol error probability? Well, we'll try to design the constellation so that the most common symbol errors induce the fewest number of bit errors. Okay, and the most common symbol error is to go from one point to the adjacent points. So if we have, for instance, a constellation with 4 symbols like this, okay, then my task is now to enumerate these with bit patterns, and I can do that in 2 different ways, or many different ways actually. So let's do the natural one. So this one is 0, 0, 0, 1, 1, 0, and 1, 1. That's the natural way to do that. This is the binary representation of 0, 1, 2, and 3. Okay, so this is naturally binary coded scheme. Let's do it in a better way. Let's do gray code. Gray code. So what do I do here? Okay, so first of all, what is the problem with this? Well, suppose I transmit this point. Let's make this in a color here. The most common errors I do when I transmit this one is to the neighbors. Okay, how many bit errors do I do when I move from the middle here and here? Well, I do here 1 bit error. Okay, maybe I should do this in a different color. Let's do this in yellow. 1 bit error here, but I do 2 bit errors when I go there. You see that? Okay. And 2 is the maximum number of errors I can do for this very simple constellation. But if you have 3 bits, the worst you can do, I have 3 bit errors. So I would like to enumerate this in a different way so that adjacent points differ at most in 1 position. And that's called the gray code. So I could do, for instance, 0, 0. And then I would like to move just 1. So 0, 1. There is 1 bit position that differs between 0, 0 and 0, 1. Okay, and instead of going 1, 0 on the next one, I do 1, 1. So I only change 1 bit. And luckily enough, at the end of the day, I need 1, 0 at the end here, and that's also 1 bit position that differs. Now, it's not completely obvious, but we can do this for any constellation. It actually goes for any size of the constellation. We can generate a gray code along a line like this. Okay, and what is the advantage of this? Well, here the difference between adjacent points is just 1 bit. So the most common symbol errors only produces 1 bit error. And in the long run, for high SNR, the bit error probability is then just 1/2 of the symbol error probability. Because when you make an error, 1 bit survives. Okay. Therefore, the bit error probability is only 1/2 of the symbol error probability. Okay, so these are called gray codes, and if we go back, okay. Yeah, you can read a little bit on this also. Can we do this in two-dimensional case also? And the answer is yes. And here's how it's done. Here we have 16 QAM, right? 16 points. So what we do then is we create a gray code along one dimension. Okay, 0, 0, 0, 1, 1, 1, and 1, 0. These are the bits. And then we do one along the other. And then we compose these two. So for this symbol, we pick 1, 0 from here and 0, 0 from here. And then concatenate those to 0, 0, 1, 0. Okay, and then the next one, here, we pick the first 2 bits from here and the second 2 bits from here, and then we continue to do this. So we fill out the constellation like this. And just to put up the Wi-Fi constellation that we talked about earlier, you see it's exactly this mapping that's done in Wi-Fi. Okay. The mapping here, there are many gray codes, so the mapping is not unique. You can start in different ways, but all gray codes have this nice property that if you go from one point, say this one, and you go in this direction, or this direction, or this direction, you only differ in 1 bit. And this is true for all the points. Okay, questions? No? Okay, so that's more or less for the physical layer. Some of the stuff on the rest of the lecture will also be applicable to some physical layers. But just to go back, the physical layer is responsible for transmitting bits from one place to another. And the main performance metric here is the bit or symbol error probability that we would like to keep low. And we would like to spend as little resources on this as possible. And the main resources we have is bandwidth and power. Okay? So we want to have high spectral efficiency and high power efficiency at the same time. You saw that there is always a trade-off between these two things. So then we decide what modulation format to use according to this. Okay. Now, if we then move up the stack, we go to the data link layer. And the data link layer, as we will see later on next week, one of its main tasks is to control errors, to do some type of error control. And this is typically done with the aid of retransmission protocols. And the retransmission protocols are a very simple idea. If I'm a transmitter, I transmit the packet, and then if the receiver inspects this packet and finds that it's in error, then it asks for a retransmission. So very much when you have a phone conversation, if you say something, the other side doesn't understand what you say. They say, what, can you repeat? And then you repeat. Or the other side says, yes, I understand, and then you can continue your conversation with the next statement and so forth. So it's basically the same idea. But for this to work, the receiver needs a mechanism to figure out whether the bit patterns they got, if there are any errors in this or not. Okay. Without knowing, of course, what the transmitted bits were, right? Because if the receiver doesn't know what the transmitter wants to say, it gets a message, but has to figure out from the message whether errors have occurred or not. Actually, this sounds more or less impossible, but it's not, right? And we will see how this is done today. Okay. So the idea here is that we have information bits, which is think of that as our payload, and then we add on that control bits or check bits. Okay. And we put that typically in the trailer of the packet. Could be also in the header of the packet, but it's something which we add as protocol overhead to protect the payload. So at the receiving end, the receiver can check these bits, whether that corresponds to the payload, and if it does, then it will accept the payload. If it does not, it will ask for a retransmission of the payload. Okay. Okay, so the main mechanism for doing this error detection is that we have some data, and think of this as the payload. Okay, and we have k bits. Okay, and for the notation, I mean, from the convention is to say that the first bit is b0 and the last bit is bk minus 1. But we have k bits here. And then we go through a block encoder, an nk block encoder. And k is the number of input bits. And n is the number of output bits. Okay. So one can think of the block encoder here as a simple, almost like the mapper we had earlier, something that for each input bit patterns, output and output pattern. Okay, so it's binary in and binary out, but the number of output bits is greater than the number of input bits. So we add bits to this. Okay. Okay, some terminology. The input is known as information bits, payload bits if you like, or data bits. And they're binary, of course. We talk about each of these bits as information bits. If we put them into a block, we have what we call an information word, or data word, or information block. Same thing. So it's a vector of binary numbers and k elements in the vector. Then we have the code bits, which are binary. And if we put them together, we get a code word. And a code word is a binary vector, 0 and 1, but n elements. Okay. The code is the number of possible code words. Okay. So it's all possible outputs here. We put that into a set, curly C, which we call the code. So how many code words are there? Well, I mean, it's there, right? So the number of code words is 2 to the power of k. Why is that? Why is the number of possible outputs 2 to the power of k? Almost. Almost. So the simple thing is that how many possible inputs do we have? 2 to the power of k, right? And this is a deterministic device. So it's like for each input there is an output. And so the number of possible outputs is equal to the number of possible inputs, regardless how you do it, right? So the code consists then of 2 to the power of k possible patterns. And each of these patterns is n bits. Okay. So since n is greater than k, the code here does not contain all n-bit patterns, but only a select few of them. Okay. And that's actually crucial. Okay. To say something about the how many code bits, how many extra bits we add, there is this notion about the code rate, and it's the ratio between k and n. So k is the number of input bits, n is the number of output bits. So if we want to have a unit for this code rate, is the number of information bits per code bit. Okay, and this is a number which is less than 1, since k is less than n. Okay. Now we would like the code rate to be relatively high, because that means that we are not adding so many bits in this process. And these bits are overhead bits. They end up in the header or trailer, and we would like to have them as few as possible to be efficient. Okay. So a very simple example of this. A very small code. We have a 4-2 block code. Okay, and this means that we have 2 input bits. So the data word D consists of 2 bits. And what are the possible patterns? Well, it's 0, 0, 0, 1, 1, 0, and 1, 1. Okay. And then we have the code word that corresponds to that input pattern. And it should be a 4-bit pattern since we have a 4-2 code here. So then it's like 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 1, 1, say. That's it. This specifies the encoder. For each possible input, we have the corresponding output in this table. We have here k is equal to 2 and n is equal to 4. We have a code rate which is 2 divided by 4 is 1/2. And if we would like to look at the code, curly C, it's the set of all possible code words, which are the patterns in the right-hand side of the table here. So the code consists of 0, 0, 0 is the first code word. The second code word is 0, 1, 1, 0. The third one is 1, 0, 0, 1. And the fourth one is 1, 1, 1, 1. Okay. Okay. Questions so far? All right. Then let's continue. And we have here, when we talked about block codes, we have a general mapping between these two. There is no particular pattern to this imposed by this. But we will immediately go to systematic block codes, which are heavily used in practice without any particular loss in performance or no loss in performance in theory. So systematic block codes, what are those? Okay. Again, the input is the data word and the output is the code word. It's just that the input, the code word, consists of 2 distinct parts. Essentially, the data word is the first k bits of the code word. Okay. K bits. And the last bits in the code word, which is n minus k bits, because the whole thing should be n bits, these are the parity bits, or check bits. So how is this done internally? Well, you take the data word and basically just pass that through. So that will be the first k bits in the code word. And then there is a unit here that says check bit calculation or parity bit calculation, something like that, that spits out this bit pattern of p bits, and that's stuck in the back here. So with the mux thing here basically takes this first and this later on, and then forms the output. So a systematic code word, a systematic code has code words of the following form, where the first k bits here are the information bits, and the last n minus k bits are the check bits. Okay. So this is a special case of the general block code, but it's a good special case in the sense that we don't lose any performance by imposing this structure. Okay. So my question to you now is the following. Is this a systematic code? I see somebody nodding.
Yeah, I guess.
Yeah, right. Because the first two bits, 0, 0, are the first two bits here. 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. Right? And if you look at this, you see that the last two bits is basically the input bits in reversed order. I just did that because it was easy for me to remember. Not that this is a particularly good code, right? But these are then the parity bits. And here we have the data bits. Okay. Now, typically these are a different number of bits. Okay, it just happens to be 2, 2 in this case. Yeah. Typically, this is much larger than this one. Okay, so this might be, 1,000 bits, and this might be 32 bits. Okay. All right. Shall we continue? So let's talk a little bit on how to think about bit errors. So we know, okay, so these code words here are the ones which are actually transmitted. These bits are formed at the transmitter and then put on the channel through the physical layer we have, and then will be received at the receiver. So the code words here are then sent to some type of modulator. And then goes over a channel, and maybe there is some noise on this channel, N of T. And then we form the received signal, and then we have some type of demodulator. And the demodulator spits out a bit pattern. Let's call it Y. Okay. Ideally, C and Y is the same bit pattern if there are no errors. But if there are errors due to the noise here, C and Y will differ. Okay. And a simple way to model the input-output relationship between C and Y when it goes over one of these channels that introduce bit errors is to have something that looks like this, where we take a error pattern, let's call it E, and we add that to the transmitted bits modulo 2 to get the output Y. Okay. So Y, the output, is C plus the input plus the error pattern E. Okay. So first of all, when it's like these boldface, it means vectors, so n-bit vectors. This plus with the circle is modulo 2 addition or XOR. Okay, so that means that 0 plus 0 is equal to 0. It's not very exciting. 0 plus or 1 plus 0 is equal to 1. Still not very exciting. But the interesting part is when we have still not exciting when it's 0 plus 1 here. Then it's 1, but 1 plus 1 is equal to 0. Okay, so that's the new thing here. And the reason for this is that these are bits, and these are bits, and these are bits, and the only way to make that work is to use modulo 2 arithmetic. Okay. Now, we see here that if this corresponds to a code bit, say C0 for the first bit, then if this is the error pattern's first bit, we see that when the error pattern bit is 0, the output is equal to the input. Right? So 0 plus 0 becomes 0. Okay, so then this is equal to C0 in both cases. So 1 plus 0 is 1. So when the error pattern is 0, no error. However, when the error pattern is 1, we make an error. Okay, so this is not equal to C0. If this is C0. Like this. Okay, so if we look at an error pattern like this, maybe it looks something like this, 0, 1, 1, 0, 0, 1, 0, something like this. We know that there are errors occurring in the second bit, third, fourth, and fifth bit. But the first bit, the third bit, fourth bit, and sixth bit, no errors. Okay? So it tells us what the position of the bit errors are for the transmission of the code word. And it also tells us how many there are. Right? So in this case, it happens to be 2-bit errors in the code word, and it happens to be on the second and fifth positions. Questions? No. Okay, so let's take 15 minutes and then continue.